We present POCO, which stands for 3D Pose and Shape Estimation with Confidence. Given a single input image containing a person, POCO is a novel framework that can be applied to common human pose and shape regressors, extending them to estimate the method's confidence in the result. Confidence is represented by the color of the mesh. The regression of 3D human pose and shape, or HPS, from images is becoming increasingly accurate. Unfortunately, no regressor is perfect, and accuracy can be affected by ambiguous image evidence. For example, ambiguity can arise from occlusion and motion blur. Most current HPS regressors, however, do not report the confidence of their output, meaning that downstream tasks cannot differentiate accurate estimates from inaccurate ones. Prior work has dealt with uncertainty by estimating a distribution over simple body parameters. The uncertainty of these methods can be computed by drawing multiple samples from the distribution and treating the standard deviation of samples as a measure of uncertainty. Such an approach has two drawbacks. First, it is slow, since it requires multiple forward passes of the network to generate multiple samples. Second, it trades off accuracy for speed, which means that the more samples taken, the better the uncertainty estimate. Hence, we propose an approach that directly estimates uncertainty in a single forward pass. We take inspiration from RLE, a state-of-the-art method that estimates uncertainty of human joints in a single pass. RLE models the output error using a normalizing flow as a base density function, or BDF, which is shared among all the images. However, the single shared BDF used to model the pose error of all images assumes that all these errors follow the same distribution. This is not true for a model trained with multiple datasets. To address these issues, we introduce POCO, a novel framework with dual conditioning strategy that can be applied to common HPS regression methods to estimate a 3D body together with the method's uncertainty. This effectively upgrades existing methods to output uncertainty with no downside. POCO's dual conditioning strategy consists of two components: image-conditioned BDF and pose-conditioned scale estimation. Contrary to the single shared BDF used in RLE, POCO conditions the BDF on image features. This enables it to adapt to the differences in the image and pose statistics across datasets. This, in turn, allows us to train POCO with multiple datasets. We also note that uncertainty is not just about image features. The pose of the body is also relevant, which is why we condition the uncertainty network on both the image features and body pose. We experimentally show that this further improves the pose accuracy. We apply the POCO framework to three different HPS regression methods, namely HMR, PARE, and CLIF. In addition to upgrading these methods to directly estimate uncertainty, we find that training with the POCO framework actually increases the accuracy of each of these methods by a modest amount on 3DPW test set. We perform a qualitative comparison of the original deterministic HPS regressors with their POCO version. First, we compare PARE with POCO-PARE. The arm pose in the first row is more plausible in the case of POCO-PARE when compared to PARE. We also compare CLIF with POCO-CLIF. In the first row, POCO-CLIF gives a more plausible leg pose than CLIF, while also giving an estimate of its uncertainty. We also compare POCO with recent probabilistic HPS methods, which model distributions over body parameters. First, we compare POCO with PRO-HMR. Note that the uncertainty measure for PRO-HMR does not vary irrespective of pose output. Next, we compare with Sengupta et al.'s method. They estimate per vertex uncertainty. In the first row, the torso region for Sengupta et al.'s method shows a high confidence even though the pose estimate is inaccurate. While improved pose accuracy is a welcome byproduct, we show the usefulness of uncertainty estimates in two downstream tasks. First, we show that uncertainty estimates can be leveraged to enable HPS self-improvement. For example, we take the CLIF regressor trained using POCO and run it on the charades dataset that has no 3D pose ground truth. Usually, this dataset would not be useful for training a 3D body regressor. Using the POCO uncertainty estimates, we take the frames with uncertainty less than 0.3 and treat the output simple parameters as pseudo ground truth. We then add this new confident image and pose pairs back into training. This increases the richness of the training data. We find that this self-supervision further improves pose accuracy. For our second downstream task, we automatically detect and remove the uncertain pose estimates from a video sequence using POCO's uncertainty estimates. Then we inpaint the 3D bodies for uncertain frames using glamour. Here are some results. When the woman bends, POCO detects the implausible pose, which is replaced using glamour's infilling method. Similarly, Implausible pose due to occlusion is detected by POCO and is then replaced using glamour. In summary, POCO is a novel framework that can be used to augment existing HPS regressors, such that they also produce an estimate of their uncertainty with modest increase in pose accuracy. The code and models are available for research.